Okay, so in previous lectures on this chapter, Fermat's little theorem, we have discussed Fermat's little theorem, and then we have discussed some consequences of that theorem at 14.1, and then we have talked about finding the kth roots of modulo m, or just to solve the equations of this form. Okay, so we have given a solution and then we have given a proposition to solve these kind of equations, and we have said that there is a unique solution. Now then we have proved that, and then we have also said something for the product for two distant primes. Now we are going to talk about something which is very useful and important for the next chapter on secret codes. Okay, so in the next chapter, we will talk about or introduce to some very clever secret codes that are used in everyday life for the secure transmission of sensitive information. The secret codes are based on some of the theory of prime numbers and congruences. And these we have already covered. Now, for practical use of the codes, one of the basic requirement is the ability to find very large prime numbers using a computer. And when we say large prime numbers, we are talking about prime numbers with more than 200 digits. Okay. Now, the key is to have a good primality test. That means that you have a number and then you have a way of testing that number, that whether that number is prime or not. So we have to have a good primality test. So we say that given a very large number n on a computer, we want a method that the computer can quickly apply to tell whether this number n is prime or not. So we have discussed some such test before, and that is known as Fermat's test. So which says that using the method of successive squares, test whether the a power n minus 1 is congruent to 1 mod n for a reasonable number of values of a. If this is false for any of these values a, then n is not prime by Fermat's little theorem. However, if it is true for all the tested values of a, then while it is rather likely that n is prime, if it is true, then it can be possible that n is prime. It is not definite, but we are not sure about it. Because there are numbers n, such as 561, for which a power n minus 1 is congruent to 1 mod n for all the integers a co-prime to n, yet n is not prime. So, however, there is a neat variant of the Fermat test that does work in practice, and it is based on the following simple fact. So let's talk about that simple fact. And we write it as a proposition. Proposition 14.4. We say that let P be a prime if A is an integer such that A square is congruent to 1 mod P, then A is congruent to plus minus 1 mod P. Perfect. Let's give the proof. So assume that A square is congruent to 1 mod P. Then P divides minus A square minus 1, which is equal to A square minus 1 is equal to A plus 1, A minus 1. Hence, by proposition 10.5b, P divides either A plus 1 or A minus 1. In other words, either A is congruent to 1 mod P or A is congruent to minus 1 mod P, which is the proof of this proposition. Now, if we consider this result, so then is the variant of the Fermat's test known as Miller's test. So let's discuss now the Miller's test. Miller's test for checking the primality of large numbers. So we say that let n be an odd number. Odd positive number. Okay. To be tested for primality. And let b be a positive integer less than n. B is less than n, known as the test. First, test whether b power n minus 1 is congruent to 1 mod n. If this is false, we know that n is not prime. Okay, cool. and we will stop. Right? If it is true, we work out b power n minus 1 over 2 mod n. Okay. If this is not plus minus 1 mod n, then n is not prime by proposition 14.4. Then n is not prime by proposition 14.4. And we say that n passes Miller's test with the base p and a star. Okay. If it is minus 1 mod n, we say that n passes Miller's test with base p. So I think we should mention this here. And we say that n fails Miller's test with base p and a star. This b is base, okay? If it is minus 1 mod n, we say that n passes Miller's test okay? And if it is one mod n, then we repeat and work out b power n minus 1 over 4 mod n, assuming 4 divides in minus 1. And minus 1. Now, if this is not plus minus 1 mod n, then n is not prime. And fails Miller's test. If it is -1, mod n, and passes Miller's test, and if it is 1 mod n, we repeat. This time b power n minus 1 mod over 8 mod n, assuming 8 divides n minus 1. We carry on repeating this process. One of the following 3 things will happen. 1, at some point we get a value that is not ±1 mod n. 2, at some point we get -1 mod n. 3, we always get 1 mod n until runs out of powers of 2 to divide in -1. Until we run out of powers of 2 to divide n -1 by, in other words, we get b power n -1 over 2i is congruent to 1 mod n for I is 0 to s, where n -1 is 2 power s dot m with m odd. Okay. Now, if one happens, we say that and fails. One is this, fails Miller's test. And if 2 or 3 happens, we say that and passes Miller's test. Okay, perfect. Now we can give an example. When given example 14.2, we have seen, or at least I've told you, that it is impossible to show that 561 is not prime using the Fermat test. That is not prime since a power 560 is congruent to 1 mod 561 for all a coprime to 561. But if you do Miller's test with base 5, you will find at the first state you will find at the first step that 5 power 561 minus 1 over 2 is equal to 5 power 280, which is congruent to 67 mod 561. Hence, hence 561 fails Miller's test and is not prime. Okay. We now know that if n fails Miller's test, then it is definitely not prime. But what if n passes the test? Here is the crux. Clever, but not too difficult. So let's write that. Those two lines. We know that if n fails Miller's test, then it is definitely not prime. What if but what if n passes the test? So here's the crux. So if B is chosen at random, means choose any random number chosen at random, and n is not prime. B is the best, okay? N is not prime. Then the chance that n passes Miller's test with base B is less than 1/4. Hence, if we do the test with k different bases, chance n will pass all k tests is less than 1/4 of power k. Hence, if we do the test with k different values, different bases, the chance n will pass all k tests is less than 1/4 power k. So taking k is 100, this chance is 1/4 power 100, which is about 10 power minus 60. And this is less than the chance that your computer makes an error in its calculation along the way. To summarize, we now have a powerful probabilistic primality test for a large integer n. Pick at random 100 positive integers less than n and do Miller's test on n with each of these is the base. If n fails any of these, it is not prime. If it passes all of them, then n is almost certainly a prime. The chance of getting the answer wrong being less than the chance of computer error. For a discussion of this and more powerful test, see the book by K.H. Rosen listed in the further reading at the end of this book. So let me summarize this chapter. So to summarize, we now have a powerful albeit probabilistic primality test for a large number or large integer n. So pick at random 100 positive integers less than n and do Miller's test on n with each of these is the base. Is the base if n fails any of these tests, it is not prime. And if it passes all of them, then n is almost certainly prime. Because the chance of getting the answer wrong being less than the chance of a computer error is enough evidence to show that n is prime. Thanks so much. See you in the next lecture.